Our lecture today starts a new module in our class, where up until this point, we've dealt really with rate laws, batch reactors, PFRs, and CSTRs. But now we're going to transition and to start talking about catalysis and catalysts and how those are integrated into reactors and how they behave. Now, a good place to start, I think, when talking about catalysts is where we started at the very beginning of the semester in our first class, where we have treated all reactions essentially as homogeneous up until now. And if you remember, right, homogeneous essentially meant that a reaction in a vessel occurs everywhere in a single phase. And because of that, it occurs homogeneously, right? The reaction is occurring everywhere. But for many reactions, their activation energy for self-reaction, right? If you just put the reactants in a reactor, they wouldn't react, right? So their activation energy for self-reaction is very, very high, even under thermodynamically favored reaction conditions. So, I mean, maybe an example would be, let's say you put methane and oxygen in a balloon. They wouldn't combust unless they were given either additional energy to do so, or there was a catalyst there. Like if you put a flame there, right? The balloon would pop and then the gas would light. But if you just had them together without a spark, nothing would happen for the most part. And so that's an example of needing some extra driving force to force that reaction to happen. In that case, it's thermal. But we also could reduce the activation energy for those reactions by adding a catalyst. And a catalyst is a substance that increases the rate of a chemical reaction without undergoing any permanent change itself. And the idea behind adding a catalyst is often that you do reduce the activation energy. And now there are different forms that catalysts can take. So one such form is a solubilized liquid. And a really good example of that is that there are acid catalyzed reactions. However, the most common form for a catalyst are not dissolved, right, or solubilized, that they're dispersed and often solids. And so there are two types of catalysts that I put in this category. One are enzymes. And of course, we are full of enzymes, and all of the complex chemical reactions that occur inside of our body are facilitated by those enzymes. You also could think of it from a processing perspective, where a couple of lectures ago, I talked to you about my experience working with a microbrewery. And sort of my expertise in the brewing area is related to the wort kettle, which is where the barley is added into essentially what is a CSTR. And the barley's added with very hot water, and the barley's been milled. And what happens is that it extracts starches and enzymes. And then the enzymes react with the solubilized starches to then break them down into sugars. And then after that reaches the point that you're satisfied, you then move that to the fermentation tank. So enzymes are maybe one very good example, and enzymes are everywhere. Another example of a solid catalyst are particles. And oftentimes, if you want to distinguish where enzymes are active and where particles are active, enzymes are almost always active just in the liquid phase. And I don't know whether you think about it that way, but our body is basically a liquid phase. And particles act either in liquids or in the solid phase as well. or they are solids. And so they act, maybe that's not the best way to say it, but they are active in the gas phase also. Okay. And because of this, if you think about this, that an enzyme is going to interact with some solubilized thing, right, in water, it itself being a solid, particles that might act as catalysts might be implemented in liquid or gas phase reactors, just like we've talked about throughout the course of this semester. And what happens then is that these require the interaction between two different materials that are comprised of two different phases. So the reaction actually happens at the interface between phases. And because there's two phases, or at least multiple phases, there could be more than two phases, we call these processes heterogeneous. And you might have heard the term heterogeneous catalysis. And that really just means the interaction of a catalyst with a solvent phase, whether that's gas, liquid, et cetera, and it's facilitating a reaction. Okay. Now, on these surfaces, reacting species have to interact with the surface somehow, right? They're not just kind of floating around and the surface doesn't play an amorphous role in their reaction. In fact, what the surface does, or what the catalyst surface does, is very, very specific for each one of these reactions. And so this interaction between the surface and the reactant is often called adsorption, right? And adsorption is when a species forms a chemical bond with a substrate, right? Or in this case, the catalyst. And there's two types of adsorption that we'll just mention here. The first one is physisorption. And physisorption is very weak bonds, something like van der Waals attraction. And the second type of adsorption is chemisorption. And those are stronger bonds. And they can even be covalent, right? A real bond between the surface and the reactant, okay? And an example of adsorbed species can be found here, right? Where I have methane plus water giving us hydrogen and CO, or of course, methane steamer forming. And one of the things that you can see is that each of these species, whether it's methane all the way at the top right or water at the top left, they are coming to the surface, sort of sticking to it. And it is the interaction between the surface and the reactant that facilitates elementary steps. If you remember on the very first day, we talked about reactions really just being single electron transfer events. And catalysts work to change the energetics for that electron transfer, either making it easier to accept or donate an electron. But if you notice, as we look at this surface, all of the species are not everywhere on the surface. And that begs the question, if we're talking about catalysts, where do the reactions happen? And the reactions generally happen at very, very specific sites that have a specific structure or a specific electronic structure. And we call that active sites. And an active site is simply a location on a catalyst where our reaction occurs. And it's entirely possible that there can be more than one active site on the surface, because let's say methane, in this example, might not want to adsorb at the same location as water. And even hydrogen might not form, right? You may have to, in an elementary step, strip a hydrogen atom off of the methane surface. Then those atoms have to find their way to one another and at another site, and then that becomes gas phase hydrogen, just for example. Okay, so these can happen. And there's lots of different types of active sites. And so if we're talking about an enzyme, for example, that a lot of enzymes undergo a lock and key type mechanism, in that millions of years of evolution have just gotten them to this point where a very specific structure, like physical structure, has been formed that allows the reactant to bind to that very specific site and doesn't allow almost anything else in. Okay, and that's sort of depicted here on the left-hand side of the screen. Metals are a little bit different because it's more about, especially on large extended surfaces, about the electron density, that it's more about the electronic structure, not the physical structure that gives a specific site its reactivity. And that's what the picture on the right here is trying to show, is that if you had a cube, like a crystal, where would there be a high electron density, which is shown in red, and where would there be a low electron density, which is shown in blue? And not all spots then on a metal are active sites, right? The reaction doesn't just happen everywhere. And depending on the reaction, you could have things like the oxygen reduction reaction, which is one of the areas of my expertise, where, in fact, my PhD thesis was on the oxygen reduction reaction, where it is highly reliant on crystal faceting. So it happens on large, flat, extended surfaces. So there are specific active sites, but it wants it to be a large crystal. And that's sort of pictured a little bit here on the left-hand side from this paper, where you can see water molecules that are adsorbed specifically at certain places, but it's homogeneous and the surface is relatively flat. There are other reactions where nothing happens on the extended surfaces. In fact, what it really needs is an uncoordinated site, right? Something that's not fully bound in all directions. And those are edges and defects. And that's here on the right-hand side. At least the edges are shown on the right-hand side here, where, not every surface is atomically flat. In fact, essentially no surface that you've ever come in contact with is atomically flat. So there are steps, edges, defects everywhere. And actually, for a lot of reactions, these step edges are extremely, extremely active. Now, for metallic catalysts, if we want to increase then the activity, right? That's really what we call increasing the rate of a chemical reaction by using a catalyst. You're increasing the activity. Well, obviously then the reaction rate is not just a function of the reactor volume anymore, right? Especially in these systems. Now, that means that our reaction rate is now a function of really two other things, right? It is a function of the mass of the catalyst that's there, okay? But if the reactions are happening on the surface, it is also a function of surface area. And surface area is, something that in a chemical reactor where you're implementing a catalyst, like in a packed bed reactor, we really try to balance increasing surface area with other things. And I'll talk about that in a second. But what we normally do is we try to increase the surface area generally. And because of that, we don't use just big blocks of metal, okay? I mean, if we put a huge chunk of copper or cobalt or platinum or whatever the catalyst happens to be for our application, having these huge chunks are not helpful for us. So the thing that we do instead is to increase the active area. We make particles. And those particles fall, at least I think, into two categories. So there's nanoparticles. And of course, nanomaterials and the application of nanomaterials has received a huge amount of attention. There's a bunch of faculty in our department that work in this area. In fact, all the way down from nanoparticles down to single atoms. Somebody like J.R. Regalbuto does a lot of work on single atom catalysts. Whereas in industry, it's very difficult oftentimes to deploy a nanoparticle because first of all, the processing to make nanoparticles is often complicated, and complicated as a chemical engineer means expensive. And so you can price yourself out of the application that you're looking at. But the other problem with nanoparticles is aging, is that all catalysts undergo aging processes where there's things like catalyst agglomeration and that kind of stuff that can happen. And think about most of the reactions that we've discussed in our class and that you've discussed until now in your career, that they're happening at hundreds of degrees C, even up to 800, 900, 1,000 degrees C. And there's just a lot of energy for surface movement of atoms and that sort of stuff in chemical reactors at high temperatures, and nanoparticles just don't hold up very well under those conditions generally. And so what happens is that in industrial catalysts, oftentimes we're not talking about nanoparticles, we are talking about micron-sized particles. And we could be talking single microns, tens of microns, hundreds of microns. Now, both of these increase the active area. The interesting thing about these micron-sized particles is that they don't just have external area. So these particles are a combination of internal area, which comes from porosity, and external surface area. Okay. And as we move through our semester, we're going to talk about catalysts that possess both internal and external surface area. And we're going to try to figure out how not just the kinetics behave at these different active sites or based on the location of the active site, we're also going to do stuff related to mass transport. Okay, so we're not going to dive into that, at least not for the next few lectures, but that's coming where we're going to start talking about catalyst structure and porosity and then trying to understand how mass transport and catalysis balance inside of a chemical reactor. So that'll be pretty cool. Now, you can't just put a bunch of micron-sized particles in a reactor. If you did that, you heated it up to 800 degrees, you would end up with this huge block that we said that we didn't want. So what we do is we disperse catalysts, and we disperse them on a support material. Okay. And there are lots of different types of supports. There's very common ones like alumina. That's a very, very common one. Titania is very common. Silica is very common. Ceria is also very common, right? These are really, really common in chemical reactors. In some applications where you need electronic conductivity, like in electrochemical applications, carbon is a very common catalyst support. Or sometimes what you'll do is you'll form a strange phase of one of these materials above to make it, or you'll dope it to make it electrically conducting. But carbon in electrochemical applications is by far the most common. And so alumina, titania, silica, ceria, carbon. These are where the money's at. And there's lots of different geometries for these support materials. And I'll show you, the geometry of some of them that you'll find in industry. So you'll see in the bottom left, there's beads that come in various sizes, right? So here's beads here. We also have carbon, which is right here. And we also have catalysts can be supported in monoliths as well. And that's what these are called. So these are like honeycomb and other shaped monolith materials where you would coat the inside of the pores of the monolith. So like the catalytic converter in your car looks a whole lot like that does. Okay. And there's a there's a palladium-based catalyst inside of your catalytic converter that then removes the NOx, so that way your car can pass emission standards. Okay, and what we'll do oftentimes is we'll decide on using a specific catalyst for an application. We'll find a support material that that gives us the desired properties, whether that's thermal, or in a case like ceria also has some redox activity. It can accept and donate electrons as well. So it's very good for like the water gas shift reaction. And we will implement them in reactors. And the act of doing that is really the difference between a plug flow reactor, right, or PFR, to a packed bed reactor. Or PBR. Okay. And one of the interesting things that we'll talk about in a minute is that when you go to the packed bed reactor and you require a catalyst for any reaction to happen, the reactor volume is not the thing that matters anymore. Right now, it has something to do with the amount of catalyst that's there. And we're going to circle back to that in just a second. And so here's a couple of pictures from your book that talk, or that give a schematic for a packed bed reactor. So you can see here on the left-hand side, it shows a monolith, and then the monolith, well, at least to me, this looks like a monolith that it has catalyst on it, or you can pack it, this part of this picture to me looks a little bit more like there's a bunch of sphere particles, which is a catalyst that is packing the reactor, hence packed bed reactor. And another configuration is shown on the right-hand side, where you feed the gas in, the gas comes out the top, and the catalyst isn't in the monolith, but it's on the surface of these shafts that are going throughout the reactor. Okay, so that's where the catalyst is in that case. And there's all types of packed bed reactors, whether it's gas flow, liquid flow, whether you have co-flow of gas and liquid, where like a trickle bed, where you have a packed bubble flow bed type reactor. There's lots of different packed bed reactors that we could talk about during the course of the semester. But for the most part, we're going to treat them very homogeneously. And we're going to build on this idea that the math for a packed bed reactor is very, very similar to a plug flow reactor. And as I mentioned a moment ago, that if we have a reaction where a catalyst is required, we totally disconnect the rate from volume. Okay, so for catalytic reactions, right, rate and volume are linked, but it's not a direct link. Okay. Actually, what happens is that if we were to take the volume and allow the length of the reactor go to infinity with no catalyst, the reaction rate would equal 0, right? That's absolutely not what we want, right? We still have no reaction. So what matters then is that the amount of catalyst is the thing that's going to drive the rate. Okay? And what we then want to be able to do is that, well, we still have a reactor volume. And so we have to develop some relationship here between the amount of catalyst and the reactor volume. And then we're going to use that to learn how the amount of catalyst drives the reaction rate that's here. And to do that, maybe in the most simple way, let's revisit a very common reaction that we've talked about before, where A just goes to B, right? And it has some reaction rate constant, K1. And we've talked about this before. Now, the thing that we're going to see in a minute is that for a catalyzed reaction, we're not going to use just K1. We're going to use K1 prime. And I'll explain why in a minute, but I won't do it now. And if we think about a packed bed reactor, it's just a PFR with catalyst in it, right? So we just have a cylinder and we're flowing gas. And we're going to operate a packed bed reactor also at steady state. Because of that, the math is the same. right? And we're still beholden to the exact same mass balance equation that we had before, that in minus out plus generation equals accumulation. If you remember, for a plug flow reactor, we said FA0 minus FA plus RAV equals 0. And for a PFR, we just called this minus delta FA, right? And we knew that this was really the effective volume that we had passed through as the reaction occurred, right? And so we ended up with an expression that minus delta FA plus RA times delta V equaled 0, okay? And now, if we think about this in terms of the units, remember our reaction rate is moles per liter times seconds. The change in the volume was liters, right? So we like to have moles per second, and that matches exactly what we would like there, okay? Now, the volume, though, in a packed bed reactor, we just said a moment ago, doesn't matter. The thing that matters is the amount of weight of catalyst that we've encountered in passing through that volume. So we're going to define a new term called rho B, and we're going to define that as the mass of catalyst per volume. And we're going to say that's equal to delta W over delta V. Or delta V equals rho B, equals delta W over rho B. And we're going to implement this as minus FA plus RA times delta W over rho B is equal to 0. And then we're going to define RA prime as equal to RA divided by rho B. And the reason that we do that is we want to change the units. RA prime now has units that are related to the mass of the catalyst to match this. And we'll go through the units in just a second, right? And so we end up with an expression that minus delta FA plus RA prime delta W is equal to 0. And just like we did for the PFR case, when we took the limit as the volume went to 0, now we're going to take the limit as delta W goes to 0. And our design equation for a packed bed reactor is then just DFA dW equals RA prime. Okay. And now we have a relationship between the weight of the catalyst and our new reaction rate. And you would imagine that the new reaction rate, and there's some new reaction rate constant affiliated or associated with it, and somehow you can change between the two. And that's absolutely correct. So if we think about this, right, we had before that RA was equal to K1 times CA, for example, in this example where A goes to B. Well, here we're going to say RA prime just equals K1 prime times CA. And K1 prime just has the units of K1 divided by rho B. And so the units for K1, we remember for at least our simple reaction here where A goes to B, is seconds to the minus 1. Well, now we're going to divide K1 by rho B, which has units of the chain of the mass of the catalyst over the volume. So K1 prime has units that are slightly different. It's volume per mass times time. Okay. And we'll deal with reaction rate constants, at least for these first order reactions that have units of volume per mass per time. And of course, if we have a reaction mechanism that's a little bit more complicated, or a reaction where it's not just first order in one reactant, right? just like we did for PFRs or batch reactors or CSTRs, the units will get a little bit more complicated. But the idea here is exactly the same. Now, what I'd like to do is just to solve a packed bed reactor example. But before I do that, I want to open it up to you guys so you guys can ask some questions about the stuff that we've talked about so far, whether it's about the definition of a catalyst, its implementation, or then how that changes the math we've been doing from PFRs to PBRs. Okay, if there are no questions, then let's do an example, okay? Let's take a gas phase reaction in an ideal packed bed reactor. A plus 2B goes to C. The reaction here is first order with respect to B and zeroth order with respect to A. The packed bed reactor is operated isothermally, isobarically, and stoichiometrically at 200 degrees C and 8 bar. The total molar flow rate entering the reactor is 90 moles per minute. We have a reaction rate constant, K1 equals 0.023 liters per kilogram minute. And we're asked, what is the catalyst weight that is needed to reach 80% conversion? Okay. All right. So in our example here, right, we have A plus 2B goes to C. And the first thing I'm going to do in this problem is the first thing that we've done throughout the semester here, and that is determine the rate law. And so we're told in the problem statement that the reaction order with respect to A is 0th order, and the reaction order with respect to B is first order. And so that gives us an RA prime, right, equal to minus K1 prime times CB, right? And we can do the same thing for B, right? RB prime is equal to minus 2 times K1 times CB because we're taking the reaction stoichiometry into consideration. And then finally, RC prime is just equal to K1 prime times CB, okay? So if you think about this, we've basically taken the problem statement and we have the reaction orders. So now the next part of the process is then completing the mass balance. And we just derived the mass balance for a packed bed reactor, right? DFI dW equals RI. I mean, I know that we did that just for A moment ago, but of course it's generalizable. So we have an expression, right? DFA dW is equal to RA, which is equal to minus K1 prime times CB, okay? Now, of course, from here, there are a number of ways that we could go about solving these problems. Now, one of the ways that we've done this before is by converting everything into conversion. And I've done several examples where we did that. So I'm not going to do that here. I'm going to solve this first example problem instead of by converting, FA to concentration and then converting everything to conversion. I'm going to go the other way, and I'm going to convert the concentration of B into flow rates, just to show that we can solve problems explicitly in terms of flow rates. And we talked about doing that when we did PFRs. Now we know that the flow rate of some species I, right, is equal to the volumetric flow rate times the concentration of that species. So I'm going to use that and substitute that the concentration of B is just the flow rate of B divided by the volumetric flow rate. And so here, right, DFA dW then is equal to minus K1 prime times the flow rate of B divided by the volumetric flow rate, okay? Now, this is a gas phase reaction, and we know that we're losing moles, right? Because A plus 2B goes to C. So the volumetric flow rate is not, or is going to change, right, as we go down the reactor. And again, that's another thing that we talked about. We did a derivation with respect to overall flow rates, but then we simplified that in terms of conversion. So I want to solve this without going to conversion. So now we're going to revisit that and get an expression for the volumetric flow rate as a function of flow rates, or as a function of the flow rates of the molar flow rates of each of the species. So to do that, we're going to start with the flow version of the ideal gas law. We're going to say that PV over P0 V0 equals FRT over F0 times R times T0. And we were told in this problem that the pressure is constant, right? It's isobaric. And that'll be something to talk about later on as well. We're going to do a lot of problems here where we assume the pressure is constant. And in a plug flow reactor, that's fine. In a CSTR, that's pretty good. In a packed bed reactor, it takes a lot of pressure to push the gas through the catalyst bed oftentimes. So note that the constant pressure assumption's pretty darn good for PFRs. For packed bed reactors, it's not always great. And so we'll do a couple of example problems throughout the semester where we actually take the pressure drop in a packed bed reactor into consideration. But we won't do that today because that'll overly complicate things. And so then we know the R's cancel and we're told it's isothermal. So the T's cancel. And then we're left with an expression that V over V0 then just equals the total flow rate over the initial flow rate. And that is then equal to just FA plus FB plus FC over F0. Okay. And so then our volumetric flow rate equals our initial volumetric flow rate times FA plus FB plus FC over the initial volumetric flow rate. And we actually know what V0 over F0 is because P0 V0 equals F0 R T0. So V0 over F0 just equals R T0 over P0. And so that gives us an expression for our volumetric flow rate here of RT0 over P0 times FA plus FB plus FC. And so that helps us to simplify our mole balance, right? DFA dW is then equal to minus K1 prime times P0 over R T0 times FB over FA plus FB plus FC. Okay, so there is our mole balance for A in this process. And now we just have to do this for the other species, right? So DFB dW is then equal to, if you remember, RB was minus 2 times K1 prime times CB. And everything that we did here holds for B, right? Because we were just, all we did was we replaced CB with FB over the volumetric flow rate, and we found an expression for the volumetric flow rate. And so this just becomes minus 2 times K1 prime P0 over RT0 times FB over FA plus FB plus FC. And then we do the same thing for C, right? So DFC dW equals, and if you remember from above, that RC prime is just minus RA prime because of their stoichiometry. And this becomes just K1 prime times P0 over RT0 times FB over FA plus FB plus FC. Okay. So for this example, we've taken our mole balance for a packed bed reactor that we derived earlier and just applied it to the flow rates of A, B, and C. And now the functional forms are a little bit complicated, right? We have coupled ordinary differential equations. And so every time this semester that we've had coupled ODEs, what did we use to solve the problem?
The Euler's method.
Exactly. We used Euler's method. And you guys should be pretty good at that at this point. And so I did that. I applied Euler's method to this problem. And here are the plots for the concentrations of A, B, and C, and the conversion as a function of the catalyst mass. Remember, now the volume, the reactor volume, doesn't really matter so much anymore, right? It's about how much catalyst we had available. So the Y or the x-axis now is catalyst mass, not volume. And we were asked in the problem what catalyst weight we needed to reach 80% conversion. And so I calculated the conversion the same way that we have this whole semester. So conversion is just 1 minus FA over FA0. And I found in the plot where the conversion was equal to 0.8. And that was at a catalyst weight of 103 kilograms.